Okay, so now for the level 3 problem. So let S be a set. Let S be the set of all 1,000 element subsets of the set of the positive integers from 1 to 2018. And so we want to find the expected value of the minimum element of a randomly chosen subset from S. And so, first of all, we should realize that the minimum element can at most be equal to 2018 minus 1000 plus 1. And that's because, and this is only attainable in one case, which is just 2018, 2017, and so on. And this would have 1,000 terms. 1,000 terms. And so if we calculate this, we find that this is equal to 1,019. And so that means that the possible minimum elements range from 1 to 1,019. Okay, and so now if the minimum is equal to 1, then the remaining 999 elements can be chosen from 2 to 2018. So any 999 of these can be chosen. And so this is a total of 2017 choose 999 ways to do this. And the total contribution to the expected value here is just 1, is multiplied by 1, because the value of the minimum here is just 1. And so next, when the minimum is equal to 2, then the numbers can be anything from 3 to 2018. And so similarly, the number of ways to do this is just 2016 choose 999. And the total contribution this adds to the expected value is this times 2. And that's because the minimum value is equal to 2. And so in general, when the minimum is equal to k, then the other 999 values can be chosen from k plus 1 to 2018. And so this leaves behind a total of, and so this is a total of 2018 minus k numbers. And so that means that there's a total of 2018 minus k to choose 999 ways to choose the sets, a set of 1,000 values with the minimum being k. And so the contribution to the expected value that this has is just a multiplier of k, because the minimum value is k in this case. And so what that means is that the total expected value is the probability multiplied by the value that you'd get, but it can also be the total number of successful value. Okay, hold on for a second. Sorry about that. So the expected value can just be thought of as 1 times, so when the minimum is equal to 1, the actual contribution to the expected value would be 2017 choose 999 divided by 2018 choose 1000. And the reason for this is because 2017 choose 999 is the number of ways that the minimum value can equal 1. And the denominator, 2018 choose 1000, is the total number of ways to choose a random set of 1,000 elements, a random subset of 1,000 elements from the set of 2018 elements.
我叫你妈去那个弄完水到那个篮子上。
Sorry about that. Okay, so this is the total contribution that 1 adds to the expected value. And so now the total contribution in general for K would be K times the number of ways to choose a subset of 1,000 elements from the 2018 elements, such that the minimum is K, which is this number, divided by 2018, choose 1,000. And so that just means that the expression we're trying to find out is just equal to 2017, choose 999 times 1, plus 2016, choose 999 times 2, plus all the way to 999, choose 999 times 1019, all divided by 2018, choose 1000. And so the numerator here is equal to, so we can think of it like this. So 999, choose 999, plus 1000, choose 999, plus 2016, choose 999, plus 2017, choose 999, plus 999, choose 999, plus 1000, choose 999, plus all the way to 2016, choose 999. And so in this manner, we can just repeat downwards until we get to 999, choose 999 on one row. And so the total sum of these is just equal to the numerator here. And so if we just directly look at these vertically, we just have this value. So now we can look at each of these horizontally in row. And so by the hockey stick identity, the first column would be equal to 2018, choose 1000. And similarly, the second row would be 2017, choose 1000. And eventually this just goes to 1000, choose 1000. And so that means that this is equal to 2018, choose 1000, plus 2017, choose 1000, all the way to 1000, choose 1000. And so if we apply the hockey stick again, this is just equal to 2019, choose 1001. And so that just means that the fraction here evaluates to just 2019, choose 1001, divided by 2018, choose 1000. And so now, using one of the definitions of n choose k, which is n factorial over k factorial times n minus k factorial, this is equal to 2019 factorial divided by 1001 factorial times 1018 factorial, divided by 2018 factorial divided by 1000 factorial times 1018 factorial. And so this is equal to 2019 factorial divided by 2018 factorial times 1000 factorial divided by 1001 factorial. And so this is equal to 2019 divided by 1001. And so that's the answer. So the other question is, show that there are at least 2n plus 3 not necessarily distinct prime factors of 7 to the 7 to the n plus 1 for all non-negative n. And so you can do this by induction. And so the base case for the induction it says non-negative n, so the base case would be n equals 0. And in this case, 7 to the power of 7 to the power of 0 plus 1 is equal to 7 to the power of 1 plus 1, or 8. And so 8 equals 2 cubed, and so in the base case, there are 3, which happens to equal 2 times 0 plus 3 prime factors. And so now, onto the inductive step. And so for the inductive step, it's basically just showing that x to the 7th plus 1 has 2 more prime factors than x plus 1. And so, in other words, this is also basically just saying that x to the 7 plus 1 divided by x plus 1 is composite. Oh, this is at least 2. And so, of course, there are some restrictions on x, because this obviously isn't always true in general. And so, I claim that x equals, as long as x equals 7 to the 2m minus 1 for some integer m, then it would work. Then this is composite. And so the way this works is that x to the 7 plus 1 divided by x plus 1 is equal to x to the 7 plus 1 is equal to x plus 1 to the power of 7 minus x plus 1 to the power of x plus 1 to the power of 7 minus x to the 7 plus 1 divided by x plus 1. And so this is equal to x plus 1 to the power of 6 minus x plus 1 to the power of 7 minus x to the 7 plus 1 divided by x plus 1. And so now we can use the binomial theorem here and then subtract out these values. And what that would get is that this is equal to x plus 1 to the power of 6 minus 7x to the 6th plus 21x to the 5th plus 35x to the 4th plus 35x cubed plus 21x squared plus 7x divided by x plus 1. And so if we do this division, we find that it works cleanly, and this is just equal to x plus 1 to the power of 6 minus 7x to the 5th plus 14x to the 4th plus 21x cubed plus 14x squared plus 7x. And so we can factor out a 7x here, which would bring it down to x fourth plus 2x cubed, 7x times x to the 4th plus 2x cubed plus 3x squared plus 2x plus 1. And now this can be shown to be equal to x squared plus x plus 1 squared. And so now, so since we had x's in this form, so we can substitute 7x with the term 7 to the power of 2m. And so that means that this is in the form x plus 1 cubed minus 7 to the m times x squared plus x plus 1 times x plus 1 cubed plus 7 to the m times x squared plus x plus 1. And so in order for this to be composite, it's sufficient if to show that both of these are greater than 1. And so first of all, clearly this is greater than 1. So we just need to show that this is greater than 1. And so basically just x plus 1 cubed minus 7 to the m times x squared plus x plus 1 is greater than 0. And so this expression is at least equal to x plus 1 cubed minus 7 to the 2m minus 1 times x squared plus x plus 1. And so the reason for this is because m is already greater than 1. This is already guaranteed. And so 7 to the 2m minus 1 will be greater than 7 to the m. And so subtracting out 7 to the 2m minus 1 is smaller than subtracting out 7 to the m times the same thing. And so now we can substitute this value back in for x. And so what that gives us is x cubed plus 3x squared plus 3x plus 1 minus x cubed minus x squared minus x, or 2x squared plus 2x plus 1. And so clearly this is greater than 1. And so that means that both of these terms are greater than 1. And so that shows that this statement is true. There are always at least 2n plus 3 not necessarily distinct prime factors of 7 to the power of 7 to the power of n plus 1 for all non-negative n. Okay, so thank you everyone for coming. And so we'll see you next week. And next week there will also be a guest lecturer.